Hi class. In the last video, we set out our motivation for and kind of the derivation of the method of Frobenius. And now I'm going to summarize the method and how we use it to find a solution around regular singular points. So our example here, so I've got this table from the book up, and I will kind of refer to it back and forth while I do the example. So let's start off. Here's our equation. So let's go through the table and do what it says to do. So we'll do step A, and that's to figure out what P of X and Q of X are. So to put this kind of in our standard form. So our P of X, we're just going to divide everything by X squared, and P of X is going to equal negative X over X squared, which equals negative 1 over X, and Q of X equals 1 minus X over X squared. So we see that X equals 0 is a singular point because you've got a 0 in the denominator there. But if you multiply P by X and multiply Q by X squared, then you get X P of X equals negative 1, and X squared Q of X equals 1 minus X are both analytic. That's a Y at X equals 0. So that's how we have that X equals 0 is a regular singular point. Okay, so that's everything. Step A is just sort of verifying that. Alrighty, step B. Now, I actually don't like this list. There's a step that I want to do before B. So step B is taking our guess that our solution is going to look like x to the r times an analytic function times a power series. But we actually know how to find r because of this indicial equation. So I'm going to insert a step before B. We're going to solve the indicial equation. And that's what they do in the examples in the book. So I'm not really sure why, they put this down here when the indicial equation falls out of step C. But I think it'll be more useful if we solve it first. So I don't know what to call this. Let's call it step B. I have no idea. We'll call it step beta. Sure. So we're going to solve the indicial equation, which I'll write out. So this is the equation, but what are P naught and Q naught? P naught is the limit as x approaches 0 of x times P of x, which equals the limit as x approaches 0 of negative 1. So it's negative 1. And then similarly, Q naught is the limit as x approaches 0 of x squared Q to the x, which we've got right here. We just plug in x equals 0. This equals 1. So we can sort of rewrite our indicial equation like this. R minus 1 minus R plus 1 equals 0. And that gives us an R squared minus R, so minus 2R plus 1 equals R minus 1 squared equals 0. So our R's, we have a double root at 1. Double root. Now, um, back when we saw the Cauchy-Euler equation before, it mattered, and when we saw characteristic equations before, it mattered when we had a double root, because that made it hard for us to find like a second linearly independent solution and all that sort of things. We're going to come back to that. I'm going to discuss that a little bit at the end, but for right now, it doesn't affect us. We're just trying to find one solution. We know that this r equals 1 is gonna work for us. Okay, so our next step, I'm going to make this really small for a second, and then I'll fix it at some point. So now we're on step B for real, where we're going to have our solution that looks like W of R of X equals X to the R times N equals 0 to infinity, A and X to the N equals the sum. We're just going to combine all these, and A n X to the N plus R. Now, we know what R equals. R equals 1. We could plug this in here. And the only reason that we're not is that in another case, if we had two separate roots to the initial equation, two unique roots, or two distinct roots rather, then we would need to be doing this step twice, and we'd plug in R equals R1 and R equals R2 each time. And so it's sort of useful to have the 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 computations that we're about to do and have R called out explicitly. And so that's what I'm going to do. In theory, you could, in this case, or in any case, you could just plug in your R value, and it might simplify things a bit. So I'm gonna make a little bit more space, and then we're gonna plug this in to our equation, which is part of step B. All right, so I've got my table still, and I've copied the original equation over on the right-hand side. So now we can plug in, and we'll get this equation. And if we kind of multiply, multiply through by those x and x squared, we end up getting these terms. So we want to be able to combine these all, and it's just this last one that's going to give us a little bit of trouble. So we want this to look like let's say we want them all to be k plus r. And for the first three terms, we could just change the n to k, and that would work. But for this one, we want n plus r plus 1 to equal k plus r. And that means that n plus 1 equals k, or n equals k minus 1. So then, let's do green. This sum can then be written like the sum from k equals 1, because when n is 0, k is 1, to infinity, a k minus 1 times x to the k plus r. So let's combine all these things together, and we get, so one of the first three start at n or k equals 0, and this one, the last one, starts at k equals 1. So we're going to still write them out separately for a second, and we get this. So now the way that we can put this together is that we can single out the k equals 0 term and then put all the rest of them together. So then we end up with, when k equals 0, we get r minus 1 minus r plus 1 times a naught plus this big sum. All right, it's really kind of long. And so this is all equal to 0, so all the coefficients are equal to 0. And so here's why the table doesn't have you solving the initial equation in step, before step B like I did. And it's because it falls out right here. So this equals to 0, which we already have, because we are assuming that a naught equals is non-zero. And then these are all equal to 0. And these are the equations that are going to help us figure out what all the a's are, and then we'll get our answer. So this one implies that r equals 1. We already figured that out. And this one gives us, we can simplify this down to, so the stuff in the brackets right here is equivalent to, and you can verify this, k plus r minus 1 squared. So this whole thing gives us the recurrence relation k plus r minus 1 squared ak minus ak minus 1 equals 0. So that means that, I mean, this is pretty straightforward. If you know ak minus 1, then you can get the next ak. So if you've got a0, which you just kind of assume is an arbitrary constant, then you can get all the rest of them. And you can actually do this explicitly, like ak equals 1 over k plus r minus 1 squared a k minus 1, or k bigger than or equal to 1. Now, this does really seem unnecessarily complicated because we already got r equals 1. And again, the reason that that I left it as k is because sometimes we might have two values of r, or I left the r in here because sometimes we might have two values of r, and we then want the formula that we could plug either one in. But next, and let's take a look back at our table and see what steps we're on. So we already did step C, and I didn't even write it down. Okay, so that was setting our coefficients to 0. So that was step C right here. And then finding a recurrence relationship with step D. So this was step D here. And next, we're going to do step E, which is actually plug in R. And this is saying to do the larger root of the initial equation. And we'll kind of see why that is later. But well, okay, we'll just do it because it says to. So this is step E. E. And we're going to plug in R equals 1. And that gives us our relationship AK equals 1 over K squared times AK minus 1 for K greater than or equal to 1. And so we get that if we plug in a couple values, we get A1 equals A0, A2 equals 1/4 A0, A3 equals 1/36 A0, and if you think it out, you get a general form 1 over K factorial squared A0. And so we're just about done. Wait, let's go see our steps. Step F is actually, here's your solution that will be defined in terms of your R and your first coefficient A0. So we can write that out. Step F, our solution is, we called it W of R comma X, but it's actually equal to W of 1 comma X. And we could also write it as Y of X, because that's really what we're looking for, is A naught times X of, and then we have our whole sum of 1. So we have an A naught and everything, so that's why we pulled it out. And then we get 1 plus X plus 1 over 4x squared plus 136x cubed, etc. And so I wrote it like this because this is our x to the r, and this is our, our analytic function, an x to the n. And so we can then simplify this down and use our recurrence relationship to get our kind of closed form solution, which looks like this. We're using k. We do k equals 0 to infinity 1 over k factorial squared times x to the k. And that's for x greater than or equal to 1. There we go. That's our answer. All right, so we've got one more bit of theory, and I'm going to prove or I'm not going to prove it, I'm going to state Frobenius's theorem, which tells us something about where these solutions converge, so that you kind of know how far away from that singular point this solution is going to work. So let me write it out. All right, so this theorem says that there is, if you have a regular singular point to this equation, then there is at least one series solution of the type that we were finding associated with the larger root of the initial equation. So that's why we took the larger one before, because the theorem said to. We also get that the series converges. It tells us the like radius of convergence for that series solution. So if you had, a number line and you had your singular points here and here, then you would take the larger one and get a series, get a series solution for it, and you know that its radius of convergence is going to be here. Like you can go out as long as you're not going to like run into any more trouble. And that gives it to you. So in the example that we had before, that would say that, so remember what our equation was: x squared y double prime minus x y prime plus 1 minus x y equals 0. We only had one singular point, so x equals 0 is the only singular point. And so that actually tells us, maybe we should extend it out further, that the singular point was here, and there's no other singular point, so actually the radius of convergence would be infinity, right? Because you're not going to run into trouble anywhere else. So, okay, a couple other things. We didn't really talk about if R is complex, although like everything like sort of works the same. You just have to do more complex analysis. And this sort of thing comes up a lot. Like this concept is you're definitely going to see if you go on to take complex analysis. So and even this like larger root, you can make senses in the distance between complex numbers. So that's fine. Now, this theorem only tells us that we can find at least one series solution. It doesn't tell us anything about finding a second one. You might think that you could use that second root, but that's not necessarily what we can do now. And of course, certainly in the case where we have a double root, then that doesn't help us out. We're going to not talk about how to find a second solution in this course, just because we're going to move on to some more material, to different material, but that sort of is more effort, just like we had in chapter 4, where maybe we could find one solution and finding a second one was going to be more effort. It's always harder than you want it to be. All right, so that's pretty much it for Frobenius's method, and that's it for chapter 8. So next time we will move on to partial differential equations in chapter 10.